Hello and welcome back. We all kind of have this intuitive sense of what it means for two shapes to be similar. They look the same, just one is bigger or smaller. But what does that actually mean in the world of mathematics? Today we're going to break down the precise rules behind it all, similarity transformations.
So we say same shape, different size, but that's a little vague, isn't it? How can we be super precise about it? How can we prove it? Well, math gives us a really powerful and exact way to define similar, and it's all about a specific kind of journey from one shape to the other.
Okay, take a look at these two squares. Our eyes tell us instantly, yep, they're similar. One is just a scaled-up version of the other, for sure. But if you had to prove it in a geometry class, how would you actually do it? Just saying they look the same is not going to cut it. We need a method, a process, and that's exactly where transformations come in.
All right, so to build that proof, we need to open up our mathematical toolkit. And inside, there are two key types of transformations that are basically the secret ingredients for creating similarity.
And here it is, the official definition. A similarity transformation is either just a dilation, that's just a fancy word for resizing, or it's a combination, what we call a composition, of rigid motions and dilations. So any two figures are similar figures if, and only if, you can find one of these transformations that perfectly maps one right on top of the other.
Now, this is where we really break down our toolkit. On one side, you've got rigid motions. Think of these as moves that don't change the figure's core identity at all. You're just sliding it, which is a translation, flipping it, a reflection, or spinning it, a rotation. The shape and the size stay exactly the same. But then, on the other side, you have dilation. This is the game changer. It's the one that changes the size, and this is so crucial, it preserves the shape. It's our resizing tool.
So the best way to think about it is like a recipe. The rigid motions are for positioning. They just move the shape around. The dilation is for scaling. It shrinks or grows the shape to the final size you need. You combine them to get your final result, a perfectly mapped, similar figure.
Okay, theory is great and all, but let's actually see this in action. We're going to perform a similarity transformation, following that recipe step by step.
Here is our plan. We're starting with a triangle, and we're going to do two things to it. First up, a rigid motion. We'll translate it or slide it 5 units to the right and 1 unit up. Then, step 2, a dilation. We're going to make it bigger, with a scale factor of 2.
And this visual just illustrates the whole process perfectly. We start with the blue triangle ABC. Step 1, the translation, slides it over to become that red triangle. Notice it's the exact same size and shape, it's just in a new spot. Then, step 2, the dilation, expands it by a factor of 2, and it becomes the final green triangle. So, the original blue and the final green triangles, they are now officially similar.
Okay, now that we've seen how to build a transformation, let's flip the script. This time, we're given the start and end points. Our job is to put on our detective hats and figure out exactly what transformation happened.
All right, team, here's our case. We've got this big blue trapezoid, PQRS, and we need to find the specific similarity transformation that maps it perfectly onto the small green one, WXYZ. Take a close look. What do you think the steps are? Notice anything different about their orientation?
The first big clue is the orientation. See how the side QR slopes down from left to right, but the matching side WX slopes up? They're mirror images. So our first step has to be a reflection. By flipping that blue trapezoid across the y-axis, we get the red one. And just like that, the orientation is a perfect match.
So now that they're facing the same way, the only thing left to do is resize it. The red trapezoid is clearly bigger than the green one, right? By comparing the side lengths, we find our scale factor is 1/3. A dilation by that factor shrinks the red trapezoid down and, boom, it lands perfectly on top of WXYZ, case closed.
So, we can perform transformations and we can describe them, but here's where it gets really powerful. This whole process is the foundation for proving that two shapes are similar in geometry.
This right here, this is the key takeaway. It's not enough to just say they look similar. The gold standard of proof is finding that specific sequence of moves, translations, reflections, rotations, and dilations that takes one figure and turns it into the other. If you can define that path, you've proven they are similar, period.
Let's go all the way back to our squares from the beginning and actually prove it. We start with square ABCD and square EFGH. The first step is a rigid motion. We'll just translate, or slide, the small square so that its bottom left corner, point A, lands directly on top of the big square's corner, point E.
Okay, now they share a corner. The final move is a dilation. We just need the right scale factor. So, if the small square has a side length of r and the large one has a side length of s, our scale factor is simply s divided by r. Once we apply that dilation, the small square expands and, wow, it perfectly covers the large one.
And there you have it. The proof is complete, because we found a specific similarity transformation, in this case, a translation followed by a dilation, that maps one square onto the other. We have mathematically proven that the two squares are similar. It's not just an opinion, it's a fact, based on a defined process.
So the big idea here is that in mathematics, similarity is so much more than just a casual resemblance. It's a concrete, provable relationship that's defined by a specific path of transformations. It's all about being able to give the exact directions to get from shape A to shape B.
So we just used this method to prove that any two squares, no matter how big or small they are always similar. And that leads to a final interesting question for you to chew on. What other shapes share this property? Can you think of any other geometric figures that are always similar to each other, no matter their size or where they are? Something to think about. Thanks for joining me on this one.